Okay, great. So thank you all for coming. So today it's a pleasure to have Raghav. So Raghav is a PhD student at UMass Amherst with Cameron Musco and Andrew McGregor. So he's going to tell us about a recent work which appeared at ICML this year on efficient intervention design for causal discovery with data. Thank you, Raghav.
Hi, everyone. So today I'll be talking about efficient intervention design for causal discovery with latents. This is joint work with Shivakashi Vishwanathan, Andrew McGregor, and Cameron Musco. Here's a brief outline of the talk. We'll go over causal discovery. Then I'll describe how do we recover observable graph. Then we'll go over how to identify latents, and then we'll briefly go over linear cost model. So for the problem of causal discovery, we are given a set of measured variables. Here, those are represented by V1, V2, V3, V4, and V5. And we would like to identify all the causal relations which exist between them. A set of possible causal relations is given on the right side. We also assume that there could be hidden variables or unmeasured variables which affect these causal variables. So we cannot perform, or we cannot measure, we cannot access any distribution on these hidden variables. But the effects of those hidden variables are felt in the distributions which we sample from. So our goal is to identify all causal relations, including detecting the presence of latents, if they exist, between this set of variables. So few challenges that are present for the problem of causal discovery involve how do we differentiate from correlations and causation, actual causal relations. Among those causal relations also, there could be indirect causal relations. How do we identify the exact causal link and differentiate it from indirect causal relation?
So Raghav, just to interrupt, so what do you mean by causal relations? Do you mean also the probability distributions, or you mean just the edges?
As of now, just the edges.
Okay.
I'll describe the formal model, but yeah, X causes Y, that's all. So for the problem of discovery, we are only interested in recovering the graph, not not the properties of the distribution. These hidden variables, as I've described earlier, could influence the observable variables or the measured variables, and how do we detect them, and how do we not include their influence when we want to actually identify the causal link or a causal relation. So formally, a causal graph is defined over two sets of variables called observable variables and latents. And both are disjoint, and the set of edges can be written as union of two kinds of edges. One is between observable variables, and the other is between latents and observable. So crucially, we don't assume any edge between the latents. So the unmeasured variables do not share any edges. The only edges are between measured variables and latents and measured variables, observable. I'll refer to as observables from now on. We also assume that the latents affect exactly two random variables. This is very well known as semi-Markovian model, and many past and current work include this assumption. This assumption is sort of inherent in the kind of tests which we use to recover the graph. If we have more powerful oracles, we can aim for better models. So yeah. So here's an example of a causal graph. V1, V2, V3, V4 are observable variables sharing the edges as shown, and L1, 2, L3, 4 are latents affecting V1 and V2, V3 and V4 respectively. We also define observable graph as the induced subgraph on the observable variables V. this is a useful notion which we'll come to. And yeah, for the problem of causal discovery, we want to identify the graph G, which I've shown in the left-hand side, not just the right-hand side observable graph. So learn G while minimizing some cost of interventions. I'll come to what this cost of interventions is. So what is known using observable data, observational data. By this, I mean, so you do not perform any kind of experiments on the system of these variables, underlying these variables, and you just observe the data generated from the system. We can only recover partial graph G. So we cannot recover the entire graph, only some edges. And this has been very well studied. What kind of partial graphs can be recovered? What is known as you can suppose there are a few graphs which lie, which all. So there's this notion of an equivalence class, such that all the causal graphs in this equivalence class cannot be distinguished by any algorithm which is known. And to recover the exact causal graph from this equivalence class, we need to use the notion of interventions. Note that this is true even without any latents. So even if we are given a graph, even if we are given set of variables which we when we do not perform any experiments, we need to perform experiments to interventions or experiments to recover the exact graph. Otherwise, we can only recover partial edges. So now we define the notion of an intervention.
One interruption. So this notion of equivalence class. Yeah. So this notion of equivalence class is defined for latents or only for observables?
It's defined for both. For latents, it's a bit complicated. It's over something called ancestral graph. But for observable graph, but when latents are not present, then it's defined over the actual causal graph G. So if you know this G1, G2, like all these possible graphs lie in that equivalence.
I see.
So this equivalence class represents the graphs which are faithful with respect to the data.
So this is the Markov equivalence class, right?
Yes. Okay. Yes, exactly. So yeah, given the data, we only have so much we can do. Observational data. So when we have, so now we briefly go over the definition of an intervention. This is an assignment S of variables in S, taking values in its domain, resulting in a new distribution because we fix the variables to a value and remove the randomness from them. So this is not conditioning, this is a new distribution. So if there are no latents, set of interventions that are required, that are needed to recover this G must be a separating set system. I'll describe that later, but there is a very well-known characterization for this using this combinatorial stuff, objects called separating set system. But no such characterization exists when there are latents. The main problem being latents are not very well modeled, and even when we model it, almost all the known results are over ancestral graphs, and not much is known about causal graphs, even under the semi-Markovian assumptions. So the goal of this is to understand the case of latents better. So here's the cost model which we'll consider now. Intervention on any set of variables, observable variables, or we can only intervene on observables, has unit cost. So however big the set might be, I just pay cost 1. So the goal in this model would be to learn G using minimum number of interventions. So how do we access the data? So, okay, that is our model. Now, how do we learn this G from the data? So we access the data using these test known as conditional independence test, where we test whether Vi is independent of, this can be read as Vi is independent of Vj conditioned on Z in the interventional distribution of S. This is over assignment, so I'm being a bit for every assignment I mean of Z and S in its domain. So we can do Vi is independent of Vj given Z in the interventional distribution of S. S could be phi, then we are just testing over observational data. Yeah, this Z and S are once again subsets of the observable variables. We assume that these tests are free. We do not charge anything for these tests, and we also assume that ideally we would our algorithms run in polynomial time, so they take polynomial in the size of the graph, many tests.
So it's not only just the size, not only size of S, but also size of Z you don't consider. So you can condition also on it.
Yes, there is some, I think 1 or 2 years back, there is work which is known which try to handle this using, but they assume some hard, other oracles, like more powerful oracles than conditional independence tests. They assume path oracles. But as you said, they pay that they also consider the size of Z. So this could very well be even for a binary set of random variables. This could be exponential, like the size of the number of tests to do. Yeah. Okay. First, let's start with the naive algorithm. For every node X in our graph, we intervene on all variables except X. So in the graph G, let's consider X. We intervene on W, Z, and Y. So in the interventional distribution, because these values are fixed, there are no incoming edges onto these intervened variables. So W, Z, and Y have no incoming edges. So this is the mutilated graph corresponding to that. And when we test whether W is dependent on X or not, Z is dependent with respect to X or not, Y is dependent with respect to X or not, we would have recovered the incoming edges onto X. If we do this process, if we repeat this over every variable, we would have recovered the observable graph G, because all the incoming edges to every variable are known. Every variable is known. So the total number of interventions is n. Can we do better? In general, we show no. We argue that there is no better algorithm in the sense that even to recover the observable graph when there are latents, we provide a graph on which n interventions are needed. So yeah, this sort of yeah. So now how do we?
Raghav, just to interrupt, sorry. So by the way, have you looked at our paper with me, Saravanan, Costas, and so it was a couple of years ago in Europe.
I think I looked at you consider the sample complexity of this interventional distributions, right?
No, but as part of that analysis, we also have to consider the interventions. The kind of, here you're looking at the question even without sample complexity, right? That's the basic question of how many interventions. So we also look at that, and so we get a bound of, so we look at degree bounded graphs in this unit cost model. And there we get 2 to the d times log n.
I see.
Where it's by a randomized approach, and then with the degree is bounded, we use some large local lemma to get a 2 to the d bound, which is independent of n.
I see. So okay, let me. Yeah.
So you should probably, I understand. Yeah, you're doing something different, but yeah, I think it's also relevant.
No.
I guess the lower bound that you have probably will have large in degree, right? The lower bound which has n.
Yeah, and yeah, it has order of n degree. So the reason I was going over here is these people have showed that using b squared log n interventions, where d is the maximum degree, one can recover the graph.
Okay.
You're saying there's
Yeah, so for us
another
we needed
algorithm.
also, okay, so we were wanting more because we also needed the efficient sample complexity. But for efficient sample complexity, we could get with 2 to the d log n. So not only just recover, but also then learn the distributions and.
Okay, I see. I'll take a look at it. Yes.
So just to add into that, I think the 2 to the d comes from the fact that we need to intervene on every possible assignment to the parents. Yeah, but here in CI test, I think that's not required, right? So the 2 to the d can be avoided.
Right. Yeah, so I think, yeah, for us, we are not assuming a CI oracle. You are just assuming that you get samples.
Oh, I see. Okay. So in a way, this bounds the number of interventional samples.
Yeah, so there we are working just with a weaker oracle, which just gives you samples. I mean, so you don't, so then, you can use the samples in order to maybe have a CI test.
Correct. I see. Yeah. Okay. I'll take a look at it. Cool. So yeah, using CI oracles, conditional independence oracles, what is known as d squared log n interventions suffice to recover G when D is the maximum degree of G.
This is the in degree or the whole degree?
Maximum sum of in degree and out degree, like the maximum. So it's like it's parameterized by the maximum undirected degree, but which is
Oh, I see. No, because I think we could get like, is it that we could get something which is independent of n?
Yeah, we could get
maybe
independent
exponential
of n.
in D.
Yeah, that's true.
Okay, so maybe it's independently what.
Okay. But the interventions are pretty big in the sense.
Right. Yeah. So so this is in this unit cost model where the intervention size of the sets. So they're basically you're choosing random subsets of some constant fraction of the whole graph.
Correct. So then naively, if one approaches, I think then it would be 2 to the order of n sample complexity for that.
Right. But we could do something more sophisticated. We could get like 2 to the order d without an independence on n if the sum of in degree and out degree are bounded.
That's true.
But yeah, we should probably go back and check. Like how it fits into this model.
Sure. Okay. So.
Sorry for interrupting. Sorry.
No. That's okay. So in this, when the conditional independence tests are, one can do these conditional independence tests essentially with unit cost in some sense, like not worrying about the samples. There is d squared log n, and ideally we would like to parameterize this algorithms based on some property of the causal graph, not based on the undirected properties of this graph. Like we give one such parameterization using the notion of p colliders. So we define p colliders as follows. I'll go over the definition later a bit more formally, but if there is a path between Vi and Vj such that we say Vk is the p collider for the pair Vi and Vj if it lies on a path between Vi and Vj such that there are two arrows incoming onto Vk on this path. So this is the path. And yeah, it's a collider. So there are two arrows incoming onto Vk. And also Vk is an ancestor of Vi or Vj, meaning Vk has another directed path to either Vi or Vj. So that is this. This is a directed path. So paths when we deal with causal discovery are always undirected. Whenever there is directions involved, we specify it. So this Vi to Vj path is undirected. There are directions, we just don't care about them when we define the notion.
So there are no latents here, or?
So this path can involve latents. Oh, I did not. Okay, my notation might suggest that these are only observable variables, but these, but VK is always, uh, because of semi-Markovian assumption, VK can never be a P collider. Latent can never be a P collider because there's no incoming edges onto a latent. So this is always observable. But the other variables on the path, there could be latents here, there could be latents here. So yeah, this is, then we say VK is a P collider if VK is also, VK has another path to VI or VJ.
Sorry, I have a question.
Sure.
So this does look like there is cycles in this. So are you assuming?
Oh, yeah. So that's a good question. G is a DAG.
Yeah.
This suggests that the I did not consider the directions on this path, but they are in such a way that there is no cycle allowed.
But the way you draw this, oh, I see. Okay, so that path. Okay, so it's a DAG to begin with. Okay.
Yeah, correct. Our algorithms are parameter. Yeah, we parameterize our algorithm by maximum number of P colliders between any pair of nodes. So the number of such VKs. So first we'll look at recovering the observable graph. Then we'll go over how to identify the latents. For recovering the observable graph, we go through two steps. First, we obtain ancestral graph using order of log n interventions. Then we recover parental relations from this ancestral graph. There is another notion of ancestral graph which is more involved, and this is the notion which we use. This is a simplified notion.
So I'm sorry, one more question. So I don't know what is your result though.
Oh, sorry. Yeah, I forgot to put that. So to recover observable graph, we use order of tau log n interventions, where tau is the maximum number of P colliders. Between the pairs. For identifying latents, we use order of n tau log n interventions. This might seem like this is more than n, but the lower bound which I said earlier is only for identifying the observable graph. So in some sense, this is not beating the lower bound. Not in some sense, it is not actually beating the lower bound. So the overall number of interventions is n tau log n plus tau log n. So yeah. What is known prior is parameterizing using the maximum undirected degree, and they give d squared log squared n interventions. Yeah, for identifying latent, like for both the steps.
So can you say again what are both? What do you mean by both steps? What are the two steps?
In the sense that sometimes we only care about recovering the observable graph.
Oh, I see. This is 1 and 2. I see. So you just observe the, and then I see.
Yeah. Because it's more costly to do identifying the latents.
So just one more question. So is there a lower bound on when there is latent? Now it does look like with the latent you have already n tau etc. So there must be an n square lower bound or something.
Not like tau is always less than n.
Yeah, so that's what I was thinking, that n square.
Not that I'm aware of it.
Or is it an open question? I mean, do we know that or not?
So in the sense that even yeah, it's an open question. Like okay. I'll touch upon it when we go over the lower bounds for the.
Okay, thank you.
Yeah. Yeah. So what's an ancestral graph? Basically, it's the transitive closure of the observable graph. So in the observable graph, we have WY extra edge in the ancestral graph. We call, if there's a path between W and Y, which is directed towards Y, then we call W as an ancestor of Y. And Z is the parent of Y. Denoted by, like, the set of all parents is denoted by Z, and set of all ancestors, sorry, parent of Y, set of all ancestors is denoted by yeah, and A and C of Y. So first, now we'll define how do we obtain this ancestral graph given the data, given observational, and what interventions are needed to do this. So here's the definition of a strongly separating such system. Consider all these variables. Between every pair of variables, we define two cuts. These cuts are as follows, defined with respect to the set of nodes. So for every pair Vi and Vj, there are n choose two of them. There exist two sets, S and S prime, which belong to this set system, which is a collection of sets, such that Vi is in S and Vj is not in S, Vi is not in S prime and Vj is in S prime. By this, I mean, like, Vi is cut once and Vj is cut once using S and S prime respectively. Such as if this is true for all the n choose two pairs, if there exist two such sets for every pair, then we call this separating this set system as strongly separating. And we show that we show that to recover the ancestral graph, the set system, the set of interventions that are needed must be a strongly separating system. We show it's a necessary and sufficient set. Here's the reason for sufficiency to build on intuition. Suppose we have a path V1, V2, V3, V4, and there's a latent between V1 and V4, L14. And we want to identify, we want to say that V1 is an ancestor of V4. So consider the intervention which contains only V1. In this intervention, the mutilated graph is shown as V1, V2, V3, V4. There's no latent effect on V1. We ignore the latent effect on V4. When we do the test, Vi is dependent on V4 or not, we get that it is true because of this causal path. And in the other test, when the separating set system contains V4 and not V1, we get that they are independent. So if both the tests say that they are independent, then it's not an ancestor. If one of them, if at least one of them returns that they are dependent, like only exactly one of them will return, then we conclude that Vi is an ancestor of V4. So yeah, because we don't know which direction this path goes, we have to have this strongly notion where we cut both these V1 and V4 in the way. Okay. Building on the intuition, here's our first lemma. Vi is dependent on Vj in the interventional distribution of S. If Vi if Vi is present in S and Vj is not present in S, then we say that Vi is an ancestor of Vj. As we saw earlier, if they are dependent and we intervened on Vi, all the paths are out of Vi and they go into Vj. So yeah, Vi is dependent. I'll go over the proof soon, but for that I have to define the notion of how do we connect these tests with respect to graph notion. Before that, I'll give an easy construction of strongly separating set system. Consider these n random variables. Consider the binary representation. So it's as follows. And for the first log n column, consider their binary representation. So 2 corresponds to 0, 0, 0, 1, 0, and then flip the bits for the next log n column. So each of this, so consider these representations, write them down, and each column represents an intervention. So there are 2 log n interventions that satisfy the strongly separating property. For example, if you look at these 2 marked ones, 2 is contained in the last column, but not the column over here, and 3 is contained in this, but not in this. So this is, you can see that it is strongly separating for every pair. So yeah, so we want to show that.
Right, yeah, I guess, I mean, you can also show this by a randomized argument, right? Like if you just show the random set, then like with constant 1/4 probability, it'll separate. So like, so if you take log n of these, then you can do a union bound against the n square pairs. Okay.
Exactly. Okay. But the key point to observe, I think, as you have raised also before, these sets are very big. Like each of them has n by 2 variables. And doing this conditional independence test on these could be, yeah, we are sweeping under the rug in this model, but it is a valid problem. Okay, so now how do we connect the conditional independence test with the graph with whether Vi has an edge path in the graph G? So for this, we have to go over this notion of d-separation, which if you haven't seen earlier, it involves 2 rules. We say that Vi and Vj are separated or directed separated by a set Z. This set Z is a subset of observable variables only. If every path between Vi and Vj is blocked by this set Z. If they are d-separated, then they are independent. Then they are conditionally independent. So if Vi and Vj are d-separated by this Z, if all the paths between them are blocked by this set Z, then Vi is conditionally independent of Vj given Z. So this is the property which we want. So the first rule is as follows. If the path contains, suppose the path is such that it contains Vk, which has 1 incoming arrow, at most exactly 1 incoming arrow, then, sorry, even this is true. Even this is true. Yeah, in all such cases, if Vk is present in our set Z, then this path is blocked. Only when there are 2 incoming arrows onto Vk, we define another rule. So for all other possibilities where Vk exists, if this Vk is present in our conditioning set Z, the path is blocked. Otherwise, if there are 2 incoming arrows onto this node Vk, then the path is blocked if we do not condition on Vk. So this Vk, as stated earlier, is called a collider. So what this second statement means is we should never condition on colliders if we want to block them. If we want to block the path between Vi and Vj, we should not condition on this Vk or any descendant of Vk. So, so if there's a path Vk prime between Vk and Vk prime, we can just contract this path and assume that Vk prime is accounted for by Vk and say that none of these descendants should be in this set Z. So essentially, once again, we should never condition on the collider if we want to block the path. Yeah. Now on to the
but that descendant also should not be in the path, right? Because otherwise the descendant could block.
then if the descendant is also, you mean, no, it can't be there, right? Because okay.
I see. Because it's a collider. Okay.
Because it's a collider, exactly. Yeah. I think my diagram was a bit misleading, but yeah.
No, it's perfect.
Yeah. Okay. Now, so Vi is dependent on Vj. I'm stating the lemma once again. If Vi is an ancestor, Vi is dependent on Vj. If S cuts Vi and Vj pair. So in order to show that, we have to show that if it is an ancestor, okay. If Vi is an ancestor of Vj, then we know that the path is never blocked because there's a direct path between Vi and Vj. And therefore, Vi is always dependent on Vj. If S contains none of the elements of the none of the nodes on this path, let's assume S is Vi for now. But it can be easily removed, that assumption. So the claim is if Vi is an ancestor of Vj, that is Vi has a directed path to Vj, and our interventional distribution is over just Vi, then Vi is always dependent on Vj. And now if Vi is not an ancestor of Vj, we want to show they are independent. This is the other claim. If Vi is not an ancestor. So consider a path between Vi and Vj, and we know that this is not a directed path from Vi to Vj. And we are considering an interventional distribution S, which contains Vi. So there, the latent effects on Vi are no longer there. In this path, because we have intervened on Vi, all the outgoing edges, all the edges incident on Vi in the mutilated graph are outgoing edges. And we assume that this path is not a directed path. So there should exist a collider on this path. So if there is no collider, it means that the path is directed and it's an ancestor. Because it's not an ancestor, there should exist a collider Vk on this path. And because we are not, observe that in our test, we are not conditioning on anything. We are just intervening on S. And because we are not conditioning on collider, this path is blocked. So yeah, as I said earlier, if we condition on a collider, the path is not blocked. By not conditioning on collider, this follows from D-separation. So yeah. Now we'll come to the notion of a p-collider. A p-collider is a collider such that Vk is also an ancestor of either Vi or Vj, we saw earlier. So there's a path between Vi and Vj, and Vk has two arrows into it, and Vk has a directed path. To Vi. This can be thought of as collider with conditioning set union of these parents. I won't go into detail how it, but yeah, this can also be thought of as that. So now using two log n interventions and doing this conditional independence test using the strongly separating set system, we have recovered the ancestral graph G. So all the relations we know are path relations. Now we have to recover the parental relations from these path relations. So this is what I meant earlier when we considered challenges. Like these are indirect causal effects which we want to eliminate. Like we want to identify direct causal effects. For this, we use an intuition that parents of a particular variable are never blocked. Like there is no conditioning set which blocks the parents. Every other variable, we can at least try to come up with a conditioning set. We might fail, but we can try. But for parents, we can never block their influence. So this is the intuition. Suppose there are no peer colliders, there are no latents. So as I said, parents block all the paths from ancestors to Y. So we know that for a node Y, we know its ancestors. We know that W and Z are its ancestors. We want to recover that W is not a parent of Y. So by conditioning, so the observation is by conditioning on this set Z blocks all the incoming ancestral relations onto Y. So this I can give a proof, but this is intuitive in a way. Like yeah. Okay. So for every W, which is an ancestor.
By parents, you mean the observable parents, right?
Yeah. Yeah. So this is the step where we only deal with observable graph. So so first for recovering observable graph, we find the ancestral graph. Then from ancestral relations, we want to go to parental relations.
I see. I see.
So yeah, for every ancestor of Y, we check if conditioned on everything other than the node which we are trying to check, we see if W is dependent on Y. If so, we add W to Y. This is because as I said earlier, parents are never blocked, but everything other than parents is blocked. So in this case, ancestor set of Y minus W is Z, and W to Y path is blocked by this Z. If you remember the D separation, this is rule 1. So yeah, in this way, we can recover all the parental relations just by blocking the using the ancestors minus the set. What happens if there are p colliders? So in this example, X is a p collider because of the following path. It's a collider, and it has a direct path to Y. But because we are conditioning on this set X, this path is not blocked. We do not know a priori which of them are parents, which of them are ancestors. So here the intuition says that, here the observation says that we have to condition on everything other than the variable which we are testing it on. So all the ancestors of Y. So by mistake, we could have conditioned on a p collider which is an ancestor and which is not a parent. So this will result in this test being erroneously will conclude that W is dependent on Y. Ideally, if there were no p colliders, we would get that W is independent of Y, and that's how we separate ancestors from parents. So what we argue is the only way to, not the only, one way to remove this effect is to intervene on these p colliders. If we had known a priori what p colliders are, we could have not conditioned on them. Because we do not know which ancestors are p colliders, we intervene on them. Yeah, what happens if there are latents? So again, once consider this following path, we want to say that we want to come up with a conditioning set that separates, that says that W is independent of Y. If we are able to come up with a conditioning set Z, then we would have recovered that W is an ancestor but not a parent. And all our tests here, exactly like conditioning on Z, this path is blocked. So ideally we would expect this test to be independent, but there could be another latent path which will always result in W. This path is never blocked because you cannot block a latent path by condition. You cannot condition on latents. The only way to block a path is through conditioning or intervening. So we intervene on W. So by intervening on W, this latent path effect is removed, and this test will now result in correctly concluding that W is an ancestor of Y, but not the parent. So I think Arnab, you are muted.
Yeah, sorry, I didn't understand. So you are intervening on W. So what do you mean by W is independent of Y?
So when we construct this the probability distribution, we have for every intervention of W, we have these measured variables of Z and Y.
Right.
And for each of these assignments, we construct this table. Then we do this conditional independence test over on this constructed table over all the assignments of W.
But there W is fixed,
right? Not like once you construct this table, it's not, right? Like this test, okay. When you think of it in terms of W being fixed and okay. You should not think of it in that terms. You should think of it in terms of for every fixed value of W, you observe Z and Y values. And for every such value in its domain, you have these, you have constructed this table. So this table consists of W, Z, Y, and on this table, you perform whether W is independent of Y conditioned on Z or not.
I see. Okay. I see.
Yeah, yeah. I mean, you're correct in pointing that out. Yes. Then okay. Yeah, I think as you have suggested, we will be once again looking at random interventions only. So suppose the number of P colliders between any two pairs of nodes is bounded by tau. How am I doing that time? Yeah. Suppose the number of P colliders is bounded by tau. If we pick every node with probability 1 minus 1 by tau, and we include it in our set, and we repeat this process tau log n many times, then we have tau log n interventions of pretty big size. Each of them has expected n into 1 minus 1 by tau variables. These sets of interventions, these tau log n set of interventions, will be such that with high probability between any two pairs of nodes, at least one of them will contain all the P colliders between them, along with, suppose we wish to say whether W is is parent of Y or not, then between W and Y, all the P colliders between them, denoted by PWY, along with W, are included in at least one of them. If we identify one such set, we can, using the previous argument which I showed, we can block by conditioning on all the ancestors and recover that W is not a parent, but it's an ancestor. So yeah, so the crux of the argument is finding a good conditioning set, and this conditioning set suffers from this issue due to colliders that we should never condition on colliders. And in our case, because these colliders lie in the ancestral set, ancestors of every node, we had to define this notion of P colliders. And these P colliders, if we intervene on these P colliders, it's sufficient. Yeah, here's the algorithm, which I've stated in words before. We iterate over all sets which contain A, but not with all for every VI, which is an ancestor of VJ. We look at an intervention which contains VI but not VJ, the separating property, and then we test if it is dependent. Only if it is dependent in all the interventions, it means it's a parent, because parents are never blocked. I'll probably stop now. So, okay, I'll just briefly describe how do we identify latents. If there's without edge is once again relies on the arguments which I've stated earlier, looking at P colliders, intervening on them, and conditioning on the parents. To block all the incoming paths, P colliders remove the conditioning effects. So when there is an edge between them, now we have recovered the observable graph, and we want to identify the latents between them. So the tricky case is when we have an edge between them, because in this case, VI is always dependent on VJ. We can never come up with any conditioning set under which they are separated. Or to discover that there is a latent, come with some conditioning set or some interventions under which they are separated. We can differentiate the two cases. And it is not possible. One can write down the cases and identify that. So for that, we need a slightly a more powerful tool where we test the distributions. We test whether we test the following. Consider a simple graph which is shown above. VI has an edge to VJ, and there's a latent between Lij. If and only if there is a latent, we argue that these two distributions are same. Sorry, let me repeat that. If there is a latent, these two distributions are different. So conditional distribution of VJ conditioned on VI is different from VJ in the interventional distribution of VI. So if there is no latent, both of them are the same. So here the idea is to somehow come up with condition these sets V and S, which will block the paths once again, but we use these are called Ducey tests, and we use them to recover the edges. Yeah, once again, our interventions are over P colliders and conditioning is over ancestors. So I'm reading out the question which someone has asked. I have been in experimental neuroscience for a predominant amount of my research stint. I'm new to theoretical computer science. Would it be possible to offer, and when possible, any real-time examples of the parameters that are being discussed? Ideally, we ran some simulations. Yeah, okay. We ran some simulations and we observed for sparse graphs, the number of P colliders is much less than the maximum degree. Erdős-Rényi random bipartite graph. So I don't know if this is not a real example, a real world example, but the issue with causality research, if anyone is an experimental researcher, I'm not aware of any good data set for this to test these things out on. Most people use simulations. I hope that answers. Yeah, I think I should stop here. So yeah, the takeaway point is, which I wanted to say was, yeah, so these colliders are important, and a specific type of colliders called P colliders is useful in understanding and recovering the causal graph. Like instead of focusing on maximum degree, one can parameterize it on certain interesting properties of the causal graph.
could say something about the linear cost model also.
Oh, sure. Okay. Okay. So in the previous, previously we have seen identity cost model, or when cost of intervening on any subset of variables has cost 1. But if each of these variables has a cost associated with it, then one can define any function over the subset that we intervene on. The most natural one is the linear model, where the cost of intervening on any subset is sum of the costs of every variable. So under this cost, once again, we assume that the conditional independence tests are free. They do not have any costs associated with them. But that's an interesting model too. How do we account for cost and conditional independence? So in this case, we argue. So this is another open question, where in this linear cost model, we do not know any criteria for recovering G. Not even like there's no algorithm known that we could think of also, other than trivial algorithms. So instead, we focus on ancestral graph, which I've described earlier. For this, we show that the strongly separating set system is the correct notion, in the sense that to recover ancestral graph, any set of interventions, even the optimal set of interventions, must be strongly separating. And so our goal would be to minimize the sum total of these costs, such that we also assume a budget on the number of interventions which we can make. Because if this budget is the total number of variables, then there is an easy way of, then the trivial one works. And the interesting case is when we want to perform fewer interventions. Anyway, okay. So for that, as I stated earlier, we look at these interventions in a matrix form. So for each of these variables, suppose there are m interventions, we define this corresponds to a characteristic vector of this set. What I just said earlier means that for any two pair of variables, v1 and v2, there exists sk and sk prime, which are strongly separating. This is the necessary and sufficient criteria which I described earlier. So this matrix is called strongly separating matrix, and it has an interesting property that between any two rows of this matrix, the pattern 0, 1 and 1, 0 should exist. So essentially, this turns out to be like packing this matrix with low weight codes that satisfy the strongly separating property while minimizing the cost. And this is also related to one can also think of these row vectors now, like instead of the columns as row vectors, and assigning low weight vectors to each of these nodes, such that this 1001 pattern, non-dominating property, is maintained. And yeah, this in discrete mathematics, people study it in terms using the notion of anti-chains. Whatever I've described is called an anti-chain. So the matrix which we use is built on the following intuition. Suppose we have m interventions that we are allowed, and we are given extra log n bits that we can use. Then we can make this matrix strongly separating, like irrespective of whatever this contains. Not irrespective of that. Suppose we fill this with increasing order of weights. So 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, meaning increasing order of weights. So we can do ideally 2 to the m such rows are possible. We'll stop at n. We can make this strongly separating by putting a weight indicator vector for every node, for every row. So suppose the weight of this vector is k. In the kth column, we set the bit to 1. So I'm hurrying here, but essentially this looks like something like this. So if you look at it carefully, this is a strongly separating matrix between rows which are of different weights. Between rows of same weight, there should be, one can argue that if the Hamming weight of two distinct vectors is same, then 0, 1, 1, 0 exists. So yeah, so building on this intuition, we push these weight indicator bits onto these m columns and lose a factor of 2 by doing so. Yeah, that is the main idea. Like, we look at this as not as interventions, but as assignment of row vectors to this matrix that minimizes this cost.
So what is the main result?
The main result is we come up with an algorithm that achieves, that has cost twice the cost of optimal assignment. This is like m interventions only. These are optimum cost interventions. And we can improve this to 1 plus epsilon if the cost of maximum cost is bounded by n to the epsilon. Yeah. So
what about for just for unit cost model, like where each, not unit cost model, I mean like where you're just counting the size of the.
Oh, that's a very so that's a very good question, in the sense that if you're aware of this theorem called Kruskal-Katona theorem, that essentially gives the optimal cost in that case. So when C of S is size of S, then if this is true for every set, then the optimal is given by equal weight assignment. Not exactly true. I'm skipping one step here. Row vector. So when the costs are not unit, then it's open whether this problem, the hardness is open. But when the costs are unit, then essentially, suppose if the number of columns is m, assigning them roughly log n choose m weight vectors is sufficient. This achieves optimal cost.
I'm kind of confused. What does it mean exactly in terms of intervention? So this is saying that
it's hard to think, like there's no equivalence here if you're looking for any property of the interventions.
I'm just asking, so what is the size of the interventions then? It is, so what is the size of the set that you're intervening? That is the optimal, right?
Like if all of them are of equal weight, then you would expect each of these intervention sets to be equal size.
And what is that size? That size?
One can put it in.
I'm just asking, I mean, like, so you.
Yeah.
So you showed that, like, basically going back to your previous thing, I mean, you showed that, like, for example, with the, you said the d squared log n, it's possible, but with there the size is large, right? So there is some trade-off between the size of the set and the number of interventions, right?
No, right?
So can you get d squared log n also with like very small sets?
No, because the first step, where like getting the ancestral graph is itself, it takes log n interventions, but the number of them, the size of each of them is n by 2.
And that cannot be avoided, is it? Like n by 2 is, I mean, you cannot get
smaller. So there
than...
are, I think, I understand the question. So if we care about sparse interventions where we are only allowed k many variables to be present, then there are known results which take like n by k, ignoring logarithmic factors, many interventions. So yeah, I don't know if that is tight, I forget that, but yeah, these interventions are...
I see, but isn't that kind of just trivial? I mean, like, you will take n by k means what, right? Like, you will take without any bound on the degree. So the bound degree can be anything.
Yeah, I think so. Yeah,
Okay,
yeah, I'll point out this.
Okay, maybe we can take this offline. So, yeah.
Yeah. So yeah, so 4 or 5 years back it was shown.
Okay.
It's not recent.
Is it by
but yeah.
Kashi Vishwanathan?
No.
No.
It's by Shanmugam et al. Karthikeyan Shanmugam.
Okay.
Yeah, I'll check that once and send you the link.
Okay, thank
you. Yeah. One second. The number of ones in each of them. I think it would be n by log n by, suppose the weight is k, n by k. This one also, I think so. I'll check that once, but essentially it is n by log n, which is pretty big. Okay. Sorry, I did not have time to go over this approximation algorithm. But this result is very, I mean, this is very good. Like this is purely combinatorial. It's called Kruskal-Katona theorem, and it gives us a way of identifying the exact optimal solution, and says that this is achieved with equal weight vectors, which is pretty surprising to me. Yeah. If you have any questions, please go ahead.
Is there anything that we can do if tau is not given to us a prior?
Yeah. So I did not go over it, but using doubling trick, we can get rid of that.
I see.
Yeah. So the open problems here are, there is no necessary criteria. Like what is, yeah, like I think Vinod was asking this question of what is the lower bound known for in terms of tau, or in any sorry, not in terms of tau, but what is known when we have to identify latents. So that is not known, but in general, there's no known characterization for necessary criteria for recovering the observable graph. So that is still open. And in the hardness of this result, saying that is it anti-hard, or is it, can one give optimal algorithm for the linear cost model, is also open. Other costs are anyway there, like one can define any other cost model.
thank you, Raghav. This was
Thanks.
very nice. Thank you.
Thanks. I'll go over the paper which you had mentioned, the 2 to the D. Yeah.
Yeah. So we can talk offline, I guess. About
Yeah. Okay. Thanks.
Okay. Thank you everyone for joining. Okay, so I guess the next talk will be next week by Sutanan. So we had a break of 3 weeks, so the next one is without a week in between. So we'll meet next week then. Okay, thank you all. Bye.
Thanks.